Cinda Land. I'm the acting executive director of the Mars Society. I'm going to moderate this panel. Again, the title of this panel is the Vasimir Drive Silver Bullet or Hoax. If you're not familiar, the Vasimir Drive is a propulsion system created by Chang Diaz, a former astronaut. And he has said that, or news has said that it'll get us to Mars within 36 days, I believe that was the recent report. And just let me introduce you to our panelists, and I'll let them start us off with some 10-minute intros on their take on this new propulsion system. I have to my immediate right is Rob Terry, Richard Heidman, we have Jeffrey Landis, and Dr. Robert Zubrin. Go ahead.
Okay.
You can sit down. You can sit down up here.
I'd prefer to be there.
Oh, okay.
Actually,
All right.
just for this talk. All right. Okay. Very quickly, I'm just going to try and introduce a few concepts and questions about Vasimir. I've spent some 30 years in plasma science in high-density, high-energy plasmas and low-density, low-energy plasmas. And Vasimir has always been a topic I've followed. Had it been on Twitter, I would have been a Twitter follower of Vasimir like for years, you know. And it's always been sort of an amusing bit of technology. But the issue is it amusing enough? And so I'm just going to set my own discussion. I'll give about a couple of moments, a summary of what Vasimir is. Are there conditions where Vasimir would help? How could it help? Where are its leaks and its losses? How well are the figures of merit verified for Vasimir? How do they compare with other kinds of drives that you might use in in-space propulsion? And finally, how much TRL improvement for the dollar can you get? Essentially, technology readiness levels or NASA's yardstick for when something's ready to do anything that you're interested in. How many dollars does it take to move Vasimir a few TRLs compared to something else? Okay, so let's get into it. All right. Back in 2006, myself and Tom Hill and Ralph McCartney published a study about comparative masses and energies for lunar and Martian missions. The upshot of that study was it's cheaper to put a payload on Mars than it is to put the same payload on the moon. Why? Because you can aerobrake on Mars. Do not try to aerobrake on the moon. Bad idea. So the amount of fuel that you carry to bring something to the moon costs you back in Leo. So from that paper, a figure of merit kind of winkled out in our minds called the mass advantage for Mars. And the mass advantage is really just this ratio. If I fiduciate things to sort of the mass I can throw to the moon, and then I compare how much mass can I throw to Mars for the same mission profile, for the same set of tankage fractions, for the same set of stages, everything else the same, asking how much, I have a fixed amount of mass in Leo, how much mass can I throw to Mars compared to the moon? In the example of that paper, we looked at aeroshell fractions, which I can generalize to aeroshell or EDL mass fraction. We looked at specific impulse of the driver, but not just any driver, one stage of the mission, the translunar injection or the trans-Mars injection. That's the place where you'd get most delta V for your work. Okay, that's where you have to put the most delta V into the mission. So the mass you can throw to Mars is sensitive to those two things. It's sensitive to the ISP you can use for the injection stage, either Mars or lunar, and it's sensitive to the amount of parasitic mass that hangs on your payload, your EDL mass fraction. Now, I want to point out very quickly, I took the figure in that original paper and I extended the axis of specific impulse. Up in the original paper, we looked at 900 and 1,000 or so. near where nuclear thermal rockets can sit. So I pushed it on up to see what would happen to these trade-offs when I got into the domain of Vasimir, which is 10,000, 20, 15,000, maybe even 30,000. Well, upshot is, if Vasimir was going to be useful for you, you'd think that if you walked across here, keeping fixed mass fraction and increasing the ISP, you would cross a lot of colored bands. As the more bands you cross, the higher your mass advantage goes. Lo and behold, for where Vasimir sits in this trade space, you've finished. Basically, when you go and fix the mass fraction for EDL and change only the ISP, you're saturating. When you move in this direction, you cross only a few bands. If you want to really increase the mass fraction you to throw to Mars, you fix wherever you can go in ISP and monkey with the EDL fraction. That's the way you cross more and more bands. And as it turns out, I thought these curves would maybe saturate at a factor of 3, but I don't care what I do in the transmars injection. I can have a hyperdrive in transmars injection. They all pretty much saturate at about 2.4 mass advantage to Mars. So the trade space in Vasimir's direction is weak. The trade space in fancy and better high mass EDL on Mars is strong. So my point is, even if Vasimir works, there may not be a use for it in the context for Mars. Now, the next question is, now this other set of questions, and I'll go through these quickly and we can return to them later through more details. Where are the leaks and losses in Vasimir? There's a radial plasma flow, there's a radial neutral flow in the vacuum. Radial flow doesn't do anything for your rocket. There are charge separation and accumulations of charge on the rocket vehicle. There's about a 20 volt, and at higher power and higher thrust, it might be more potential downstream of the Vasimir rocket. If you let that potential persist and you push all that charge out in space, now you've got yourself an electrostatic rubber band. You threw all this charge out there, you've got charge on your rocket. Now the cloud that's following you is trying to contract, and that's effectively pulling you back together. Whatever thrust you did to build that charge is trying to slow you down again. It's pulling you back. And so you haven't really had a net thrust with respect to your center of mass. Your rocket has to throw neutral flow. Otherwise, electrostatic forces will accumulate and you'll be dragging this big cloud of charge and it'll be slowing you down. So rockets as we know them, Huntsville thrust as we know it, always throws a neutral flow of gas, not a charged flow or a conducting flow. And so you have to be careful of that. There are radiation losses that have no particle heating. Even when you have 98% efficiency, which Vasimir advocates claim between DC and RF, that 2% is still a huge amount of radiation to get rid of and heat. There are magnetic flux dissipations in any metal that constrains the magnetic field. And so let's take a look real quickly. How am I doing on time? Okay? Yeah, okay. One real quick, the one last one. Magnetic flux, here's what Vasimir looks like in its laboratory experiment. Here's basically what it's trying to achieve. dmdt times exhaust velocity is what you get for the thrust of a rocket. Basically, it always boils down to this. Most conventional thrusters have huge dmdt and modest V exhaust, so the specific impulse is down in the hundreds, and dmdt is in the kilograms or thousands of kilograms per second. So there's plenty of thrust, but not much ISP. In the Vasimir, you have a magnetic nozzle, and I want to point out that all these magnetic field lines close on themselves. So when you push something, and if the plasma were to contact the metal, the important problem is it would quench the plasma or chew away the metal. So when you push something out the back end, the recoil has to be felt against the magnetic field, and the magnetic field has to force its recoil against the metal parts. It's the metal parts that are your rocket. If there is dissipation of energy, and let me, right here, 4 little spherical magnets, and they're all arranged like you might see them in Vasimir, in a string of little dipole magnets, like the magnets here that are forming the coils here. When you constrain these magnets and put them in a copper tube, the magnetic field is constrained, and so they fall very slowly out of the copper tube. If you were to constrain these magnets and try to trap them so that you would say, okay, I'll bounce them, and in a short copper tube, they fall right in, not very slowly at all. The reason is this longer copper tube entrains more and more of the field flux and produces a drag on the particle as it comes down. If this were a superconductor, I would probably easily levitate these little magnets in the superconductor, but it's only copper. So the point of the matter is, when I try and compress this magnetic field, there are sort of dissipative mechanisms in getting the momentum back into the metal. And so you may not get as much thrust as you think. So that's another interesting issue. So Vasimir has a helicon discharge here, which produces most of the ionization. It has an ion cyclotron resonance heating antenna here, which tries to make sure that the thrust goes out the pipe. Ion cyclotron resonance heating, of course, all ions or electrons circulate in the magnetic field. The ICRH gets a radio frequency wave in resonance with that circulation. And resonance heating is just that. It whips it around faster and faster at a resonant frequency, resonating with the Larmor frequency at that part of the magnet. And so it puts a lot of energy into the transverse temperature. This plasma is not in thermal equilibrium. It has two temperatures at least, all right, but for certain two. There's a longitudinal temperature or energy, there's transverse energy. The job of the ICRH is to pump energy into the transverse component. The job of the magnetic nozzle is to slowly move this energy into the longitudinal component, because that's what makes thrust. This is a vector notion. This is the exhaust velocity in the axial direction. If you have effective velocities, because magnetized plasma particles or neutral particles come out here and flow radially, all radial flow is momentum you've wasted. You can't get thrust out of it. So part of the issue about how to make sure all these things are done well is to understand how this is to be integrated and controlled. Okay, so basically there are a lot of issues about the efficiency of this process. Mostly Vasimir has succeeded beautifully in being a plasma physics experiment. It is the inverse of a magnetic mirror. It is like ion cyclotron resonance heating for fusion, except it's done for a different reason. So all of that works, and folks have learned a lot about this, but there are limitations in this process. There are losses in this process. There are losses about how you push on the field and then push on the motor. And so all these questions are sitting out there. And really quickly, one last thing. If you asked, what's the thrust to weight ratio? If I take a typical nuclear thermal rocket, thrust to weight ratio, and this is the weight including the fission core in the nuclear thermal rocket, thrust to weight's about 6, maybe 5, 7, in this drawing. Every design point I have found, and I wish there was someone here to stand for Vasimir to tell me I'm wrong,